yesterday is just some of the scrap notes about the concept of Boolean algebra or Boolean math or Boolean logic, all those different ways we can think about it. And we got all the way up to different types of questions you could anticipate. But let me show you the slide notes I have on this as well. Okay? So you guys can see this, and this will go into the paper notes that I'm making for you guys. So Boolean algebra is a method we're working with binary functions 0 or 1. The basic operations are and, or, and not, unlike addition, subtraction, multiplication, and division in normal algebra. There is specific notation associated with Boolean algebra so that you can write it like mathematically. When you not a variable, the general way is to put that prime symbol on there, or sometimes it's put as an overline. Okay, so X with an overline. I don't know which way the IB exam is going to go this year, so just they should at least explain it in the documentation there. Okay. So we can apply this to values, the values 0 and 1, and we can even apply it to variables. So the not operation, 1 not is 0, 0 not is 1, or you could think of it that x not is 1 if x is 0, and x not is 0 if x is 1. Okay, so that should be pretty simple. All right, this is another way we could examine it in basically a truth table. When x is 0, x naught is 1. When x is 1, x naught is 0, or vice versa, right? Okay? The symbol, you can think of this electronically, is a gate symbol that looks like this. All right, but I do have some good news for you. This is the way that I've taught for 17 years this course. But in the last few years when they changed the IB curriculum, what they say now in the IB curriculum you need to know is not that you need to memorize that symbol for the gate. It's just going to be a circle with the word not written inside of it. You can write this on your exam if you want, but you can also just write a circle with the word not inside of it. They've simplified. I don't know why they thought that was a better way to fix the curriculum, but they did, so that's what it is. Okay? Honestly, you should remember this one. When you guys go into computer science beyond this course, that's what you're going to use. Okay? Now, the AND function is essentially represented with multiplication. So just like regular algebra, you can just write two variables beside one another to multiply them, or you can use a dot. And I've even seen this symbol used for multiplication, but I do not recommend that, because that one, again, is very often confused. Some people use that for powers. So AB equals 1 if A is 1 and B is 1. AB equals 0 if A is 0 and B is 0. Again, that's the AND function. The OR function uses what you would call the addition or the plus sign. Okay? And some other notations is this one. Again, I haven't seen that one in a while, so don't bother with that one. Okay, and again, we talked about what the OR function does. Okay? There's, again, that truth table. So if I have variables A and B going through a pattern, A is 0 with and then the OR and how that relates. Now, one thing I didn't note yesterday that's interesting. If you look at just this column of and, in the column of and, there's only 1, 1. In the column of OR, there's 1, 0. Okay? So otherwise it's a 1. And then this one, it's a 1. Otherwise it's always a 0. And so that's, again, something to just sort of note about the way that goes down. Everything in Boolean algebra has what's called a dual operation. That's true in regular math as well. Like the dual of addition is subtraction, the dual of division is multiplication. They're sort of opposites of one another. And in Boolean algebra, that's even more so the case, because it is a two-state system. So what you can do with a 1, you can do with a 0, and vice versa. Okay? The general rule is the equation theorem rule in Boolean algebra always has a dual by changing and to or and changing 1s to 0, and that same equation is valid. Okay? So an equation will be valid if you flip or invert all the values, right? So all your 1s become 0s, all your 0s become 1, all your ands become ors, and your ors become ands, and the equation is still true. This is the AND gate symbol. This is the OR gate symbol. This one was a little harder to draw on a projector because they don't have one just readily available. But that's what they look like. Again, sort of a rocket ship and a plug is the way you can think of them. And an OR. And again, you don't have to remember these. You can just draw a circle with the word AND in it or a circle with the word OR in it. But I really recommend you remember those instead. Okay, so putting them into an expression is just like in regular math. There's an order of operations which can be overridden using parentheses, but the not, the and the or is the order of operations. Okay? This is very similar to regular algebra, so it shouldn't be that hard to sort of make that jump. Okay? So what gets done first in this equation? The not, right. Okay? So another way you could think of it is, if we put brackets around that, that is done first, and then, so the not's done first, and then we and it. Okay? So that's the way you could put it there. All right. It does not mean that, because that would create a different circuit. If you gave these two things to electricians, the result would be a different operation. So it's very important that we follow that order of operation, or we're going to get completely different results. Okay? So that's the wrong way to interpret what this means. Okay, so this one means this. The and is being done first, then the or. And you can see the circuit that's created. It is not this one. That's where we're doing the or first. Because again, you notice it's creating a different circuit if you do it that way. So that order of operations matters. We'll practice that in a sec. Just wanted to catch you up to kind of where we were yesterday. Okay? Okay. Now, here's an interesting one. If we go and take that to a new level, and take that out there, you should be able to take something like this. This is probably a little more complicated than the IB exam will give you, but express it in words. Express it in the truth table. Express it in Boolean algebra, or even draw it as a circuit diagram. Okay? So all four of those should be something you should be able to do. So let's try it with one here. Okay? Let me try it with the algebra first. So A naught Really? Really? I thought it was just slow. Hang on. It's one. Okay, so let's try this. Actually, I don't want to use that many variables. I'm going to go back to some others. Okay, so there's a Boolean expression. Let's see if you can express that to me in words. Okay, so not A, let me write it in, so not A and B So why don't we just say or? Okay, so now we're on this side. What should we do first? What's inside the brackets, right? So say in words what's going on inside the brackets. A or B and C. Right. You got it. You were able to express that in words. Okay? Let's see if you can go the other way. What if I gave you this in words? Okay, could you turn that into algebra? Okay, so tell me what to write. C prime. Or, yeah. Could we do this? Yep. Yep. You could also put the dot in between there to represent the multiplication, which means and. So you should be able to do that fairly easily. Back and forth and back and forth. Okay, so now what about this? Okay? If I give you a truth table of values, like I do this, okay, could you do something with that? right? Could you turn that into something? So that's a little more complicated, so I'm just saying that is possible. So you see here that how we would do that. So I'm going to show you a technique later on how to do this. It's a little more complicated, but that's the case. But it might be easier to go the other way. What if I gave you this? Okay? And if I gave you this, could you fill in this part? If I gave you the thing here, could you fill in this part? How would you do that? Well, you'd have to kind of test it, right? So if A is 0 and B is 0, okay? Actually, we'll make it this way. Sorry. Make that C. C equals this, okay? Could you fill in the rest of this table? Okay, so help me out. What would C be when A is 0 and B is 0 and A is 0? Right? So then not 0 is 1. 1 and 0 is 0. 0 or 0? 0. So now you know what goes there. What goes in the next one? Try and evaluate it in your head. On the video, on the recording now, they're just hearing mumbling in the background. Anyone got an answer? Take a shot. 50-50. 1? Okay, so let's see how it would evaluate. Okay, so this is a 0, this is a 1. Okay, so 0 naught is 1. 1 and 1 is 1. 1 or 0 is 1. You got it. Okay. What's the next one? Okay, so A is 1, B is 0. Okay, that's 0 and 0. Right? Okay, because 0 and 0 is 0. 1 not 0 or 1 is 1. Okay, finally 1 and 1. It's 1 again? Let's see. 1 not 1 or 1. 0 and 1 or 1. 0 and 1 is 0 or 1 is 1. Yep. Okay. Takes a little practice, but you guys can see how you can start doing those evaluations. Finally, turn that into a circuit diagram. So now we have this. Whoa, missed a couple. Now we have that, and we have this. We could express it in words. We've already done that. But now let's draw the circuit. Okay? So what's done first? The knot. So I'm going to draw a knot symbol. And what's getting knotted? A is getting knotted, right? What's done next? The AND gate. So I'm going to draw an AND gate. And it's the A that's being knotted that's getting ANDed combined with B. B is being ANDed. Okay? But then the next thing that's being done is an OR symbol. So, and what's getting ORed is the result of this. So this thing the result of that's getting ORed, and it's combining that with A. So I'm going to go over to A. I'm going to jump that wire and then join that wire right there. So again, think of it like wires, right? I'm jumping over one wire and I'm soldering it to the next wire. And the result is C. Okay? So with that in place, I give you this circuit. I give you this circuit. What's the Boolean algebra for it? Okay, so let's not use the symbols. This is and. This is or. This is, pardon me. Of course I did that on purpose. Not or. Okay. What's done first? A and B. Yeah, so let's put that down. A and B. What else is being done over here? Sort of right away. B or C. Now, we're not sure where that goes yet, but I'm just going to put it down. Something's getting knotted. What's getting knotted? Yeah, this whole thing is being knotted. Then what's happening? This one here and the one we just been working on are being combined with and. So in other words, it's something like that, right? This and that. And we're done. This equals D. Okay? Can you say that in words? That's right. Okay? Just takes practice. It just takes a little practice to get used to it. Okay. Now, the one that's the tricky one is the truth table one. So we're going to get to that one in a minute. But okay. So let's put it together with a real example. A car has 3 sensors built into it. Sensor K is for the key in the ignition. When a 1 is picked up by the sensor, it means that there's a key in the ignition. Sensor D means that the door is open. Sensor L means that the lights are on. The car also has a little buzzer, a little bing, 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 that goes off when B is 1. The buzzer goes off if the lights are on when the key is not in the ignition or when the door is open and the key is in the ignition. From that logic, could you create a Boolean expression? Now, this would be kind of a tougher question, but I think it's entirely possible that this is something you could think about creating in expressions and circuitry. This is a real-world problem. This is actually the way cars work. So they actually have to give that to electricians to figure out. So let me do it for you. Okay? That's the solution right there. Okay? L represents the lights, K represents the key, D represents the door, B represents the buzzer. This is the actual circuit you could give to an electrician to make those sensors work. Okay. I'm going to come back to that one tomorrow. See if you guys can do that one without me. So you're seeing ahead there. All right. The truth table for this could also be created. Now, this would take a little bit of work, but you'd be like, for all the possible inputs here. So all the times when all these are off or when one of them's on, etc., you would go and fill all this in. And you would know the times when the door buzzer would be going off. These are the 4 times the door buzzer would go off. It goes off when the door is open and the key is in the ignition. It goes off when the lights are on. It goes off when the door is open and the lights are on. It goes off when the door is open, the key is in the ignition, and the lights are on. Okay? That's the way it works. But as you look over this, the door is kind of a big deal. Didn't you say? Like, the only time when the door sensors that it doesn't go off is just when the door is open but the lights. Other than that, when the door is open, it's going off, right? So the door and one other thing makes it happen. And this is very much like regular algebra. Sometimes you don't need such a long equation to still be able to pull off the same amount of solution there. And so the reality is, as I said to you yesterday, there is actually ways to simplify Boolean algebra using some laws. But the good news is that's not part of the new curriculum for you guys. But I'm going to show you anyways when we have time. We won't have time today. Okay, so here's another example. If A is a 1, B is a 1, and C is a 0, what's the value of X in this circuit? Okay, let's see if you can just do this in your heads right now. A is a 1, B is a 1, C is a 0. So when it gets all the way down to X, is it a 1 or a 0? 50-50. All right, so let's see what happens. So right there, that's A and B. right? That's B naught and C. That is that. And then I'm ORing it. Okay? And then I'm ORing all of that. So this is the actual algebra there. Okay? For that circuit. But sometimes it's actually easier to work with the circuit than the algebra. Because let's think about how this would work with ones and zeros. 2 1s go into the AND gate, what comes out? A 1, right? 1 goes into the OR gate, what comes out? A 0. 0 and 0 go into the AND gate, what comes out? 0. 0 goes into the NOT gate, 1 comes out. 1 and 1 go into the OR gate, what comes out? 1. 1 goes into the NOT gate, 0. So that circuitry actually sometimes is easier to work with. Yes?
In this statement, you don't need to worry about C at all.
That's correct. You don't have to worry about C at all. Okay? That's where I'm going with this. You're right. Okay? So, yeah, you can do it that way. You can do it this way, or you can simplify it as well. Okay? So there are lots of ways to look at this stuff. Luckily, I'm actually pushing you guys a little beyond the curriculum here. I don't think you're going to need it. You can also do the whole truth table if you want. You can go down this truth table and start figuring out how many times a 1 is generated. In this case, here and here. Okay?
So when C is 1.
No, that's not true because C is 1 here. Yeah. Okay? All right. Here's one. Okay, this will be our last one today. First of all, can you guys say this in words? Start with Q is.
Q is
Yeah. Okay, you guys are getting really good at that, okay? Really good, although I wish the door was open so people walking by would be weirded out, but there's the circuit. That still needs a little bit of practice, I think, but you guys will get there. Okay, there's the circuit. And then from there you could build truth tables and things like that. But actually, when we look at this truth table, Q is 1 when A is 1, except if B and C are both 1, 2. Okay? Actually means this whole circuit could be simplified down to this. Okay? So the circuit could be simplified and the algebra could be simplified. So if we look at that versus this, it's simpler in math, but why is that practically a good idea? The math is one thing. It's nice in math to simplify expressions. But why is this more practical for what we're doing? Circuit is smaller. Why else? You're right. Could be faster, yeah, that might be the case. But what, in addition to smaller, you're missing a point. Less components, and what does that mean? Yeah, cheaper, right? Less components makes it cheaper, smaller, and hopefully faster. We'll talk about that and something called the delay. We have time. Okay, so it only uses 3 devices, not 7 like the original design. And that can even be simplified down to 2 devices. Here's a new one. You haven't seen that one before. So as we wrap up today, what do you think that one is? NAND. Yeah, that's correct. Excellent work today, everybody.